Hello teachers and hello students. Welcome to this mathematics tutorial series which is organized by Oromia Education Bureau. I am Dr. Garma from Matu University and our today's topic is about derivatives. The problem of finding the tangent line to a curve involves the use of limits, and in the previous tutorial we have seen that there are some 5 special limits that are very important for the development of derivatives or for differentiation. So these are a quick reminder of what we have seen in the other tutorial. And the limit of sine of x over x as x approaches to 0 is 1. Second special limit is the limit of 1 minus cosine of theta over theta as theta approaches to 0 is 0. And the third special limit is the limit of 1 plus 1 over x, the whole the power of x as x approaches to infinity is e, where e is the base of the natural logarithm. E is this number. And the fourth special limit is the limit of 1 plus y, the whole the power of 1 over y as y approaches to 0, that is also equal to e. And the third and the fourth special limits are one is just derived from the other by simply a change of variable, and we have seen that with the previous tutorial. And the fifth special limit is the limit of a to the power h minus 1 over h as h approaches to 0, which is equal to ln of a, with the restriction that a has to be greater than 0 and a is different from 1. And these 5 limits are called special limits. They are so called special because they have special advantage for the topic of derivatives, and we will see why they are special and the way they are useful for the development of derivatives. Derivatives are emanating from the need that the early mathematicians and the physicists had the interest to find the slope of a curve at a specific point, which turned out that as you pass a secant line between a point P and a Q, the slope of the line that you obtain is not basically the same as the slope of the curve, but as you move a point P and a Q together, that is Q is being moved towards P, finally these secant lines finally become this tangent line. This is a tangent line. So this tangent line, the slope of that tangent line is at least equal, will have a slope equal to the slope of the curve at that point. I want to remind you that the curve doesn't have a unique slope. Every point has its own slope. So at least we are able to find the slope of the curve at a particular point by making a tangent line to that particular point by first drawing a secant line and moving this point Q towards P until they eventually become closer enough to each other that they will only make a tangent line, and the slope of that tangent line is obtained as the vertical increment, that is f of x minus f of a, divided by the horizontal increment, that is x minus a. That is the slope of this line. And when x approaches to a, means when we move Q towards P, it becomes a tangent line, and that the slope of that tangent line is termed as the derivative or the differentiation, and it's symbolized by f prime x. When you write f prime x, it is pronounced as f derivative of x. That is the derivative of the function. And it is of great importance to have in mind that derivative is nothing more than calculating the slope of a curve at a particular point, and they are given a special name which is called derivative. So derivative which is defined in this way is simply f derivative of x is the limit of f of x minus f of a over x minus a as x approaches to a, is something which is coming from this formula, that is essentially moving the 2 points P and Q closer enough to each other. There is an alternative way of writing the same thing, but this moment it will help us to tackle some other problems. So there is a little bit of modification to it that will give us a powerful tool to tackle some part of the problem, and I will tell you later on why we need them. So if I replace this part, which is called x minus a, that is the denominator of it, by h, and then this x becomes a plus h. So if I want to rewrite the formula that I had a while ago for derivative, then I can rewrite that one as f derivative of a, which is the limit of f of now a plus h instead of f of x minus f of a over h. But now as h approaches to 0, because previously we had at x approach to a, but now because x is approaching to a means the difference between x and a, h must be approaching to 0, because x is approaching to a means they are roughly the same. So in general, at any point x, f derivative of x can be written as the limit of f of some x plus h minus f of x over h. So this is an alternative formula for derivative to this one. This is useful for some part of the problem, and in this form also it will be useful for some other part of the problem. So we will use both of them for different purposes, and I will show you later on with examples. So I want you to recognize their differences by putting them together. Once again, if I have a point here and another point there, if this is a, correspondingly I have f of a here, and if this is x, I have correspondingly f of x there. So the vertical increment is f of x minus f of a divided by, because we are calculating the slope, to the horizontal increment, that is x minus a. So f derivative of x is simply the limit of f of x minus f of a divided by x minus a as x approaches to a. So that is what we can infer from this diagram. Alternatively, for the same thing, I can write this point to be x. So correspondingly, this is f of x. I can write here x plus h. This is x plus h. Correspondingly, I can write here f of x plus h. So the vertical increment is f of x plus h minus f of x, which is the numerator here. And for the denominator, x plus h minus x plus h minus x. So they cancel each other, and I'm left with h. So the limit of f of x plus h minus f of x over h as h approaches to 0. This is one alternative formula for derivatives. This is another alternative formula for derivatives. They have different areas of applications. This part in its version like this one is better for derivatives involving powers, polynomials, radicals, and so on. In its form this way is much better for trigonometric functions specifically, and for exponential functions like sines, cosines, and so on, and exponential functions. Cosine, sines are examples of trigonometric functions. But in some other cases, whichever you use doesn't matter. In some cases, for example, for polynomials, if you use this one or if you use that one, no problem. But if you are using trigonometry, if you want to find the derivative of trigonometric functions, this one functions in a pretty much simpler steps than if you have used this one. We will elaborate that with examples next. The first example is find the derivative of f of x, which is c, that c is a constant. We directly substitute that one into our derivative formula. Our derivative formula is this one. So my f of x is c, and because here is f of x and here is f of a, my function is such that f of x is equal to c means is f of whatever is c. So f of a is also c, because that is a constant function. So f derivative of x is limit of f of x minus f of a over x minus a. So f derivative of x is the limit of f of x is c, f of a is also c, that is c minus c over x minus a. So that is the limit of c minus c over x minus a, that is 0. So for any constant function, its derivative is always equal to 0, and you have to remember that. For example, if you are given a certain function f of x is equal to 3, what is its derivative? If derivative of x is 0, because it is a constant function. Derivative of a constant function is always 0. The second example, find the derivative of f of x is equal to x. Still, I'm using the same formula for my derivative. That is this one. That is something we have derived earlier from directly definition of a slope. So f derivative of x is the limit of f of x minus f of a divided by x minus a. Because my f of x is x, my f of a is also equal to a. F of x is x, f of 2 is 2, f of 100 is 100, f of a is a. That is the way that function is behaving. So my f of x is x, my f of a is a. In the denominator, already in my formula, I have x minus a. I will just keep that. So I have to cancel x minus a by x minus a, and I'm left with 1. So f derivative of x is the limit of 1 as x approaches to a. That is 1. So derivative of the function f of x is equal to x is simply 1. Here it says find the derivative of f of x is equal to x squared. In our example, I am trying to gradually take you to a higher level, starting with a simpler example. Now f of x is equal to x squared. So f derivative of x is the limit of f of x minus f of a divided by x minus a as x approaches to a. According to this function, f of x is x squared and f of a is simply a squared. So f of x, that is simply x squared, minus f of a, that is a squared, and the denominator side, that is this x minus a, is already kept here, which is equal to the limit of, as you know in mathematics, if we have a squared minus b squared, that is always a minus b into a plus b. That is the way we factor. A squared minus b squared is a minus b into a plus b. In a similar way, x squared minus a squared can be written as x minus a into x plus b, divided by the already existing denominator here. But it happens that these two will be cancelled. I already did that. And then I'm left with only x plus a, this part. That is only this. So the limit of x plus a as x approaches to a. Now you have to pay your attention that x is approaching to a means x is nearly equal to a, or a is nearly equal to a. So I will substitute this a by x because x is approaching to a. So what is x plus x? 2x. So f derivative of x for a function f of x is equal to x squared is simply f derivative of x is equal to 2x. Later on, we will derive a very general formula for these kind of polynomial functions, but I will take you to that level gradually, and I will let you know that after some time. Here is another problem. Find the derivative of f of x is equal to 3 over x. Here again, we will use the same formula for the derivative, that is f derivative of x is the limit of f of x minus f of a divided by x minus a. According to this function, f of x is 3 over x. If we substitute a, f of a is also equal to 3 over a. According to this function, f of 2 is 3 over 2. F of 100 is 3 over 100. F of a is 3 over a. So this is my formula. It says limit of f of x. So my f of x is 3 over x. Then it says minus f of a. F of a is 3 over a divided by the denominator x minus a. I'm not affecting that part. So I will take a least common multiple of x and a, that is the product of the two, ax. Ax divided by x, a times 3 is 3a. Ax divided by a, x. X times 3, 3x, divided by the same denominator. Then this is the limit of 3a minus 3x divided by ax times the reciprocal of this denominator, that is 1 over x minus a. And then you can factor out minus 3 from this one, so that in the parentheses you are left with x minus a, so that this x minus a will cancel x minus a, and you are left with minus 3 over ax. That is minus 3 over ax is this one. So the limit as x approaches to a of minus 3 over ax, because x is now approaching to a, I will replace my a by x, minus 3 over x times x squared. So minus 3 over x squared is the answer. So if you are given this kind of function, its derivative is minus 3 over x squared. Now it says find the derivative of f of x is equal to 3 over x. Is the same problem, but now this moment I'm going to use the other alternative formula for derivative. A while ago we have used this one in order to find this as an answer. This is one of my derivative formula. Now I'm going to use the second one, that is this one. Then if I substitute into that one, and if I do this very basic mathematics, I will come to the same answer, because everything is the same. It's only a little bit of algebra in between. If you do that, you will also come to the same answer. In this specific example, I wanted to demonstrate to you that whichever formula you use, that is either this one or that one, for some problems such as this one, doesn't matter, and you can try by yourself that either case you will get the same answer, like f derivative of x is minus 3 over x squared. So we already got the derivative of y is equal to 3 over x, and if it is derivative, consequently its slope is minus 3 over x squared. Assume that you are given a certain point p of x1, some certain point x1 and y1, and then if you wanted to find equation of the tangent line, because we have said that if you are given a certain curve, this is the y-axis, this is the x-axis. If you are given a certain point there, if there is a slope, assume there is a slope here. So if you wanted to find the slope at this point, what would be the slope of that tangent line? This is a tangent line to that curve at a specific point P. The slope of that tangent line is, because from our earlier derivative formula we got the slope to be minus 3 over x squared, and now you are given this x1 comma y1, that is the point of this P of x1 comma y1. Then the formula would be y1 minus y1, that is this y1, is equal to the slope m, that is this one, into x minus x1. Assume, for example, that point P, which is x1, y1, is like 3 comma 1. Then if I wanted to find the slope of the tangent line, the line that makes a tangent to that curve at that specific point is y minus y1, that is y1 is this one, and x1 is this part. So y minus y1 is y minus 1, minus 1/3. How is this minus 1/3? Minus 3 over, the slope is minus 3 over x squared. What is x? 3 squared. And 3 squared is 9. Minus 3 over 3 squared is simply minus 1/3. So that minus 1/3 is the slope times x minus x1. So my x1 is 3. So simply by simplifying this one, that is taking this constant term to the other side and multiplying this one into the bracket, this one into the bracket, you will get y is equal to minus 1/3 of x plus 6. This 6 is called the y-intercept, minus 1/3 is called the slope. That is the way we tackle this kind of problem. Now find the derivative of f of x is equal to x squared minus 8x plus 9. If we use this formula, f derivative of x is the limit of f of x minus f of a divided by x minus a. F of x is x squared minus 8x plus 9. And the f of a is simply you substitute instead of x by a, that is a squared minus 8a plus 9. So directly substituting f of x is this one, and f of a is this part. And then by simplifying, because now you can eliminate some of the terms. This is x squared minus a squared, that is x minus a into x plus a. This positive 9 cancels minus 9. Then I'm left with minus 8 into 8a, these two terms, and then you will simply use a very simple algebra to multiply and subtract some of the terms. Finally, you will get f derivative of x for the function, this one, this derivative is 2x minus 8. You don't have to worry with this kind of polynomial derivatives of polynomials, because few minutes later I will demonstrate to you a very general approach by which you can, even by inspection, by looking at with your eyes, that you will be able to tell the derivative. I will bring you to that level, but it is a must for us to pass through these kind of exercises before we dive into the general pattern. Here is the time. Find the derivative of f of x is equal to x to the power n, and the expansion of terms like a to the power n minus b to the power of n can be written as a minus b into a to the power n minus 1 plus a to the power n minus 2b plus, and so on up to b to the power of n minus 1. That is the way we expand these kind of quantities. Then we have this general formula for our derivative. Then we will directly plug into this formula what we have. So the limit of, instead of f of x, my f of x is x to the power n. I will directly substitute. And if this is my f of x, then my f of a is, my f of x is x to the power of n. My f of 2 is 2 to the power of n. My f of 100 is 100 to the power of n. My f of a is a to the power n. So that is the way, divided by the same denominator. So that is the limit of, now x to the power of n minus a to the power of n can be expanded according to this. So I will replace these terms by these ones, as you can see there, divided by x minus a. Then f derivative of x is equal to, because these two terms can be cancelled, is x to the power of n minus 1 plus x to the power of n minus 2 times a. Everything in this parenthesis will be left. So f derivative of x is given according to this. Now I will substitute every a by x, because here we have x is approaching to what? A. And then finally I'm left with x to the power of n minus 1, x to the power of n minus 2 times x, and so on. Finally we are left with x to the power of n minus 1, x to the power of n minus 1, n terms, n such terms. So finally I have n times x to the power of n minus 1, because we have n such terms. So if I'm given a function f of x is equal to x to the power of n, its derivative is n times x to the power of n minus 1. For example, if you are given a function such as f of x is equal to x cubed, its derivative is, f derivative of x is simply 3 times x squared. That is, if there is n here, this n will become the coefficient, and then you will reduce 1 from the power n minus 1. I'm just doing the same thing. 3 here, 3 minus 1 is 2. That is the way you generally do the derivative of every polynomial. If you have this general formula, the whole previous exercises and examples we have passed through can easily be done even with inspection, if you have this formula in your mind. This is derivation of the same thing, but now I wanted to use the other formula. In this case, in the previous case, we have used this one, but this moment I wanted to use this one. So my function is again the same. F of x is equal to x to the power of n. Now, if f of x is x to the power of n, because I'm using this formula f of x plus h, if f of x is like this, then f of x plus h must be x plus h to the power of n. So here I have x plus h to the whole power of n minus f of x means the same thing, minus x to the power of n. So we have this kind of binomial expansion. A plus b whole to the power of n is expanded as a to the power of n plus n times a to the power of n minus 1 times b plus n into n minus 1 over 2 times a to the power of n minus 2 times b squared. So using this binomial expansion and directly plugging in our values into the general formula for the limits, that is this second an alternative formula, we have already plugged in the values, and then our expansion for this term according to this rule, the binomial expansion is x to the power of n plus n times x to the power of n minus 1 times h plus n into n minus 1 x into the power of n minus 2 times h squared minus x to the power of n, and this x to the power of n will cancel this one, and because I'm dividing everything by h, the remaining terms, this has 1h. When I divide by h, this term will be without h. This has h squared term. When I divide it by h, it will only have 1 power of h afterwards. So this is what I'm telling. This will be n times x to the power of n minus 1 without h, because h has cancelled by this one. This one had already h squared, but now no h. Now h is approaching to 0. As h approaches to 0, this term goes to 0 because of the h which is approaching to 0, and then I'm left with only this one. That will lead me to the conclusion that once again f derivative of x for a function f of x which is equal to x to the power of n is also n times x to the power of n minus 1, and that is a remarkable result because both of our formulas for limits leads us to the same answer. This is a derivative of a square root function. Now I want you to directly use the formula that we have derived a while ago, and it applies that if f of x is equal to square root of x, square root of x can be written as x to the power of a half, where that half is just n, and I can directly use this formula. So it is a half can be taken from the power, a half here, x to the power of a half minus 1. So directly you get 1 over 2 square root of x. That is the way we make a derivative of square root function, by directly applying the formula that we have derived over there. The 10th example is find the derivative of f of x is equal to 3 over x. We previously did this problem, but this moment I want you to do it with a general formula for power functions that we have derived a while ago. F of x is 3 over x means it is 3 times x to the power of minus 1. That is my n. So I will bring my n to the front and multiply it by this already existing coefficient, and then I will subtract 1 more from the power, then minus 3x to the power of minus 2. So it will be minus 3 over x squared. We get the same result as using the direct definition of slope, and we got the same answer. Now once again I want you to pay your attention on derivative of trigonometric functions. As I told you, two alternative formulas for calculating derivative of any function. I told you that this is not the one which is recommended for trigonometric functions, but rather this one is. But I want you to test why this is not the right option for derivative of trigonometric functions. If I'm given f of x is equal to sine x, if I directly plug in sine x into this one, because f of x is sine x minus f of a is sine a over x minus a, then I would stuck over here because I can no longer be able to simplify this trigonometric expression, and I can never make kind of substitution or kind of cancellations in order to go further. So I will stuck just over there. But rather, if I had to use another alternative for derivative of an exponential and a trigonometric function, f of x plus h minus f of x over h, if I substitute sine x into there, at least I can use sum of angles formula to expand my trigonometry. So if I substitute in sine of x plus h minus sine of x over h, I can use this formula for expanding sine of sum and the difference of angles, and the same for cosine. Then it will take me to sine of x plus h means is sine x cosine h plus now cosine x cosine h. You will directly use these ones minus the same thing sine x over h. Now I want to bring this term and this term together. They have sine x in common, and then I want to factor out sine x, then into cosine h minus, instead of this one, minus 1 and over h. I'm left with the other two terms, these two terms. I mean this one term cos x and sine h, that is cos x and sine h over h again. Limit h approach to 0 for both of the cases. When you see the one which is in this region that I have encircled it, cosine of h minus 1 over h is one of my special limits. If you remember, one of my special limits was the limit of 1 minus cosine of theta over theta as theta approaches to 0. 1 minus cos theta or cos theta minus 1 doesn't matter, but in both cases it is also equal to 0. So the limit of cos h minus 1 over h as h approaches to 0 is what? 0. So this term would be 0 and it will be eliminated. So I'm left with only this term. Here, if I take cos x outside of the limit, here I have sine h over h as h approaches to 0. This is also one of my special limits. That is the limit of sine x over x as x approaches to 0. So this becomes 1. So this term as a whole is equal to 1. 1 times cos x is simply cos x. That is the derivative of sine x. And you can appreciate how the special limits make life simpler for us to make derivatives of trigonometric functions. We will use the same procedure for derivative of a cosine function. If I'm given f derivative cosine of x to be my function, f derivative of x is the limit of f of x plus h minus f of x over h. Once again, I will directly substitute and expand the cosine function according to the expansion formula here. Then by using those special limits, they will reappear again, as you can see over here. It is very straightforward to arrive at that the derivative of cosine function is negative sine x. What is more important in this case, the key point is that whenever you are making a derivative for trigonometric functions, the right choice is this formula rather than the other one. Once you know that, the derivative and the procedure of arriving at the answer is not complicated. Here is find the derivative of f of x is equal to e to the power of x. Again, it is this one which is recommended for exponential functions as well. So e to the power of x plus h minus e to the power of x over h. You will directly substitute and you will factor out e to the power of x from there, and then you are left with this term now, which is e to the power of h minus 1 over h. As you can see, that is also one of the special limits, that is a to the power of h minus 1 over h as h approaches to 0. That is ln of a. If this is ln of a, this one must also be what? Ln of e. And the ln of e is logarithm of e to the base itself, which is 1. So this derivative must be equal to the same, e to the power of x. So these special limits, together with this alternative definition for derivatives, helps us a lot in making derivatives for trigonometric and exponential functions. Here is find the derivative of f of x is equal to a to the power of x in general. If we directly substitute that into there, you will again once again encounter this special limit a to the power of h minus 1 over h, which is already we have said it's ln of a. The consequence of this is that f derivative of x becomes a to the power of x ln a. The steps are pretty simpler. You only have to make the right choice, that is this definition for limit when you are dealing with exponential and trigonometric functions. You directly substitute. For example, in this case, you simply factor out a to the power of x as in here. Then a to the power of h minus 1 over h will be left. That is one of our special limits. that special limit is simply ln a. So this is a to the power of x times ln a. That's why we directly wrote this one. It is so straightforward, but you have to make the right choice. If you once make the right choice, everything is quite simple. Find the derivative of f of x is equal to 5 to the power of x. Simply our a is now 5, so that is 5 to the power of x times ln a. It's direct substitution. Let us recap what we have seen. With this approach, we can have one alternative for derivative of a slope. Another approach is with this setup, we can have that kind of approach. This one is recommended for sine, cosine, and exponential functions, as we have seen them with examples. And this one is good for power functions, radicals, polynomials, and so on. But in some cases, your choice is up to you, and whichever you have chosen, it doesn't matter, and both of them may yield the same answer. And derivative of any constant is 0. And this is a formula for slope. Y minus y1 is m into x minus x1, where m is the slope. This is a slope-intercept form equation of a line. If f of x is x to the power of n, its derivative is n times x to the power of n minus 1. If f of x is sine x, we have seen that its derivative is cos x. If our function is cos x, its derivative is negative sine x. If our function is e to the x, its derivative is again the same. We have seen that previously. If our function is a to the power of x, its derivative is a to the power of x ln a, with limitations that a must be greater than 0 and different from 1. This, now we move on to some exercises. Find the derivative of f of x is equal to the third root of x. Okay, the time is over. Now let us do the problem together. The problem says find the derivative of f of x is equal to the third root of x. And directly applying the formula for any power function, f of x is equal to x to the power n. That is, f derivative of x is n times x to the power of n minus 1. The third root of x means is x to the power of 1/3. So this is simply my n. So it is 1/3 times x to the power of 1/3 minus 1. So the final answer is 3/2 of x to the power of minus 2/3, or 1/3 x to the power of 2/3. That is simply by directly using this formula, we can make a derivative of these kind of functions. Second, find the derivative of f of x is equal to 4x to the power 10 minus 3x cubed plus 7x plus 100. Okay, the time is up. Let us solve the problem together. Originally, the problem says find the derivative of f of x is equal to 4x to the power 10 minus 3x cubed plus 7x plus 100. Again, directly applying our general formula for this kind of function, when f of x is x to the power n, its derivative is n times x to the power of n minus 1. So here I will take 10 to the coefficient and multiply it by 4. 4 times 10, x to the power of 10 reduced by 1. And the same procedure for the rest. And 100 means is x to the power 0. So it is 0 taken to the coefficient times 100 times x to the power of 0 minus 1. 0 times everything is 0, so the constant term, because this is a constant, derivative of the constant goes to 0. So that is the way we make the derivative of this kind of polynomial function. Thirdly, this problem says find the derivative of f of x is equal to 6 to the power x. Okay, the time is up. So let us do the exercise together. The problem says find the derivative of f of x is equal to 6 to the power x. Whenever we have a function like a to the power of x, its derivative is always a to the power of x times ln a. So here is simply my a. With direct substitution, we get f derivative of x is equal to 6 to the power of x times ln 6. I think it is much simpler, and you will be able to solve other similar problems. Fourthly, find the derivative with respect to t for the function f of t is equal to 2 over t. Apply now the limit definition instead of the general formula. Okay, the time is up. The problem says find the derivative with respect to t for the function f of t is 2 over t. This is our limit definition. Directly plugging in everything we have and referring to the exercises that we have solved in this tutorial by directly plugging in those values into our definition and doing a little bit of algebra. You can eliminate some of the terms, and finally you will get the limit to be minus 2 over t into t plus delta t as t approaches to 0. And as t approaches to 0, you will get the function to be it is delta t that is approaching to 0 in this case, not t, delta t approaching to 0. So as this delta t approaches to 0, this part will be 0 minus 2 over t times t, that is t squared, and that is the answer. So thank you very much, and this brings us to the end of this tutorial. I encourage you to have your own time to exercise until you will be confident enough to do other similar problems. Bye bye.